Algebra 2 people. That didn't come out so fast. Hey, it's time for Lección Ocho Ocho, solving abstract equations. Right? And what in the world do I mean there? Got a definition. It's an equation which has two or more variables. So, for example, exemplia gratia, science formulas such as, or math formulas or geometry formulas or whatever, remember from physical science. Yeah, E equals mc squared, kinetic energy, force of gravity, gas laws. You've got, even like I like PV equals nRT. There's another one. Area of a triangle. The pendulum. This is converting temperatures. You've got even things that we've been doing in our class. Cosine of an angle equals x over r. It's got three variables. We've seen these all over the place, and really, the main skill that you got to learn in Algebra 2 that's going to help you with like physics next year. We're going to be constantly taking these things and taking an equation that's kind of phrased one way and then massaging it and moving pieces around so that we're solving for something else. Case in point, this is the formula for pendulum. T is for time or the period. That is the amount of time it takes for the pendulum to go and come back to where it started from. It's equal to, wait a second, change that. There we go, that's better. Tau times the square root of length over gravity. Well, what if you're doing a pendulum on Mars? G is going to change. Or what if you want it to be a pendulum that swings back and forth in 2 seconds? You want to solve for L, right? You know, if you're doing it on Earth, you know gravity and you know tau and you know the period that you want. You want to actually plug that in and get an answer for L, so we'd have to move all the pieces around here. You'd have to have time over tau, and then we'd have to take the square of both sides, and then you'd have to multiply both sides by gravity to get the length that you want. So you have to be able to do what I just did right there, maybe in steps, one thing at a time, but this would be solving an abstract equation. I want to pick any of the variables and then solve for one of them. Solve for any of them. Can I solve this equation for r? Could I solve this equation for x? Could I solve this equation for h? Could I solve this equation for v? Could I solve this equation for p2? Could I solve this equation for distance? Any of those ones, that is really the skill that we're talking about here. And knowing Beth and Dutch and Zach, I know that you're good at this. I know that you've got the mechanics to do this. You've got those skills in the bag. So there's a wide variety of these. Some involve square roots and squaring and halving and functions and blah, blah, blah. We got lots of buttons on our calculators, right, to do this. And this is what a majority of physics is expressing some scientific fact in a formula that you fiddle with. Our labs are going to be filled with, well, here's the formula we've been working with, but we can only do this with a stopwatch and a piece of I don't know, tape measure. And so how are we going to measure things like velocity and acceleration, right, when the equation is set up to solve for something else? Give you some examples here. Start with real basic thing, and that would be going between Fahrenheit and Celsius. I know the book does it. Your calculator can do it, but let's just go for it and do. We've got our degrees Fahrenheit equals the rule 9/5 C plus 32, and I want to solve it for degrees Celsius. All right, so just new context, right? It's not x's and y's, but this is like y equals slope x plus 32. And I want to solve this for C rather than for F. So I'm going to undo. So we subtract 32 first. F minus 32 equals 9/5 C. And to get C all by itself, we're going to multiply both sides, the whole stinking thing, by 5/9. So, more familiar, we know kind of what that other formula is, but it's just derived from solving for C rather than for F. 5/9 of F minus 32. So we want to start here. We have to subtract 32 from our Fahrenheit and then multiply by 5/9 so we get Celsius. That's what we're trying to do today. I'm going to switch back over to black here. Another one. And this one maybe a little bit more abstract because you didn't take geometry, but surface area of a cylinder. That's this, surface area of a cylinder. Maybe I'll draw a little cylinder in here so we get an idea of what are we talking about. We're talking about a cylinder equals 2 pi r squared plus 2 pi r h. That is oh boy, that's bad. Got a cylinder. We want to find out its total surface area. We have the circle on top, the circle on the bottom, and we got the bit that goes around, like on a soda can or something like that. Here's the two circles, 2 pi r squareds, and then here is the part where we're doing the circumference times the height. So 2 pi r is the circumference, twice the radius is the diameter times pi, and then h. And the question here is, though, how could we solve for h if we knew what the surface area was, but we, for whatever reason, would like to know what the height ought to be? So we've got to solve for this piece right here, and everything else gets shipped over to that side. So what do we do first? All this is attached to that by multiplication to h, so we're going to subtract this first. S minus 2 pi r squared equals 2 pi r h. And now we can do some division with everything that's not h going over here, 2 pi r. Now, the thing about this is it can actually be cleaned up a little bit because this is a little messy. I can split this up into two fractions. I can have s over 2 pi r, or tau r. Yeah, let's do that. Tau times the radius minus this over this. So it would be 2 pi r squared over 2 pi r, which can be simplified, right? If I divide 2 pi r squared by 2 pi r, I'm just left with r. And that even might be a little bit easier. I need the surface area and then go tau r, and then minus r is my height. I kind of like it. It's kind of clean, kind of useful. But yeah, that'll work. So what if I got a second way to do this problem? Let me start back at the beginning and how I could have done this a little bit differently. But this works. This is fine. It's useful. My second mode here is to realize that the factor 2 pi r is in both of these. Do a little bit of factoring first. So s equals, let's remove a 2 pi r from both sides, and that will leave me with r plus h. Now this is pretty interesting to me geometrically what this is saying. I needed to add the radius and the height together. Add the radius and the height together. That would be this and this. It's like two legs of a triangle, right? And then multiply it by 2 pi r, or the circumference. That's kind of weird sounding, but look at what we're doing here. I take this total distance here, and then I multiply it by that part around the circle. That's weird, but it's actually taking this thing and then it's saying, okay, I'm just going to twist it around. I'm going to take this shape and I'm going to rotate it around, and I would have counted up the entire thing. It's weird. It's weird, but it's interesting. Super interesting. Okay, now I've turned this into factors. I can divide by 2 pi r. I'm just going to leave the 2 pi here. Let's give pi a little respect. Divide by 2 pi r, and that leaves me with r plus h. I wanted to solve for h, so now I'm going to subtract r from both sides. So I will, and lo and behold, that's where we were before. So I just pick one of several methods, but by this point, Algebra 2ers, you've got lots of tools in the tool bag for knocking these things out. Okay, I'm going to take the same one. I'm going to do like the hardest solve here, and that would be to solve for r. And the reason why that's hard is because it's there and it's there. Okay, so what do we do here? Well, we're going to have to set this up to make it look like a quadratic because I got an r squared and an r. How am I going to do that? I'm going to move this s to the other side. I'm going to have 0 equals 2 pi r squared plus 2 pi. I'm going to write this so it kind of looks more like a quadratic minus s. Think of that r like an x. I've got a constant. I've got x squared plus, I've got another constant, and I've got r, or x, and then I've got my last number there. Coefficient, coefficient, constant. Okay? This particular problem gives you stuff to plug in. It says, let's work with, well, I guess if we look at it, we have, the leading coefficient is 2 pi. See that the next part we have is 2 pi h, and then the third part we have is a negative s. So if we want to solve this for r, we're going to think of it like a quadratic formula. We would have negative b plus or minus the square root of b squared minus 4ac over 2a, just plugging in this mess over here into there. And what's that look like? Well, negative 2 pi h plus or minus 2 pi h squared minus 4 times 2 pi times negative s. I know it's lunchtime, isn't it? Over 2 times 2 pi. Now you clean that up a little bit and you've got an answer, and it ends up tightening up pretty well. You can see that in the example. There are a couple of other ones that I want to show you. Actually, I think I might save example 4. I want to show you the toaster equation. Toasters. Yeah. Toasters, if you ever looked inside while you're waiting for that thing to slowly cook your food, it's got those little heating elements in there. And if you recall from physical science, that is, it has very high resistance. So it's all the electrons are bumping into that material and then making it heat up and glow and slowly toast your stuff. Resistance, the total resistance, is being broken up into small groups of resistance as it's run through each individual wire. And this is the equation for how you would know how much resistance to send into the toaster, and you can calculate based on some other stuff that's going to happen. So this is like a circuit. Okay, you're going to have to do some circuitry problems next year. And there's a way that the book does it, and then there's a way that I would do it. Yeah. So I would just think of this like a fraction problem. Okay? Fraction problem. And so first thing we would do is we'd look at this and we'd say I need a common denominator for these fractions to combine these fractions. So I would end up with R2 and R1 over R1 times R2. That's what that would turn into if I just do the multiply this by R2 over R2, multiply this by R1 over R1, and then combine those fractions. Then I'm going to use the next rule, and I'm going to flip these things. Fraction divided by a fraction. You've got that on your algebra sheet. This turns into R1, R2 over R2 plus R1. That equals the total resistance. And then if it asks you to solve for any particular one of these pieces, like I think maybe the book asks you to solve for R1, well, golly, we can do that. We can do some cross multiplication at this point and have that R1 times R2 equals R, that's the total resistance, times R2 plus R1. We got to FOIL this, or we got to expand this so we can get R1s all hanging out together. So R1, R2 equals, I'll call it RT here, total resistance, R2 plus RTR1. We're going to group the things with R1s together since that's what we want to solve for. R1, R2 minus RTR1 equals RTR2. And then we're going to factor out the R1. Lastly, divide both sides by this business here. We'll get RTR2 over R2 minus RT. There are several formulas in physics that follow the same type of rule. You'll follow this exact same type of thing as you're doing lenses and focal lengths. Okay, you use the same type of thing, but you've got to be able to do some symbol manipulation. You've got to be able to move the pieces around and solve for the part that needs to be solved for. That involves squaring and square roots and fractions and all that kind of stuff. Example 4 in the book is lateral surface area of a cone. It's similar to our surface area of a cylinder type of problem. It's a different formula, and you're solving for a different thing. This time you're solving for h. I'd be happy to show you that one, but I probably would like you to come in person if you need some help with that. Okay, so all of these, you're solving for a different thing using your basic tools. Just remember, these are real things this time. And so what we're trying to do is we're trying to find the relationship between these things, given the things, other things that we can, either that we're given or that we can measure or calculate. Okay, you've got in your email what questions to do. You can either ask me at the table or you come on in. I'll be happy to help you with some of the details, but that's all for lesson 88.